Miss Jody here with another video for the class Matter and Energy, or Energy and Matter. I think I go back and forth with calling them either or. So we're moving along in our lessons. I'm sorry, last week I had a little delay, so I didn't get all the lessons for all the classes done, and hopefully you got my note on that. But I was able to work on it this week. I had to do some projects at the Science Center with the animal room and emails and catching up on grading papers and journals for some of the high school classes that need to get those for their evaluations. And so I was delayed, but I want to get right back on it, and we're almost done with our studies. And so I was only going to do another video or two, one or two more, because I know everyone's getting ready to be done with their school year anyway, and they don't want to keep going on forever. And we were hoping to already be back together by now, but obviously things didn't work out that way. If you've been following along with us, I have been asking you to take your notes on a half sheet, so don't forget to do that, so that I can glue them right underneath the title there so you have your notes done. I still am hoping to get back together. I know that the stay-at-home order is going longer than expected, and we may not be able to be together in May, but I'm hoping maybe beginning of June we could get together for like 1 or 2 weeks to do some activities and just to have like an end of the year time party of some sort. So I'm still hoping, but if it ends up being that there's no way possible for that, then I will just have to make a pickup spot for your journals. I am making a drop-off spot at the front of the Science Center where the dig pits are. There's a crate right by the door that I'm going to open up so that you can put your note sheets if you live by, and if you want to, of course, it'd be optional. Some people have been taking the notes for a while now, would like to drop their notes off so I could get them glued into their journal. So if you want to do that, you could put your notes that you've taken so far, or any of your homework that you need to turn in, or any of your art projects that I had to go along with the journal, and put them in a little baggie, either a Ziploc bag or a like a gallon Ziploc bag or like a Walmart bag, and just write your name on it somehow, and that way I know it's you and I'll get that in your journal. But again, that would be optional. You don't have to do that. That's only if you would like to. You can save all your half sheets until we can get back together. That's another option. And I can glue them in that week. Maybe the first week we could get back together, do some activities, do some more experiments, and then I could take the pictures and all that. And then during that week, I could print out the pictures, get them in the journal, and glue in the rest of the half sheets that you did from home. And then the following week, we could meet and have a celebration, maybe a picnic outside, and do some just fun fellowship time together. So I'm still hoping for that, but if it doesn't work out, I understand. And again, that would also be optional, so some families might not feel comfortable with getting back together at all, and I would totally understand that too. Okay, but we'll stay in touch through the Google Classroom and then also through email. Okay, so moving on, we were studying the last few weeks just as a review. We're moving on to light, but as a review, if you remember, we started looking at waves, and we said there's certain characteristics to waves: wavelength, amplitude, frequency, speed, all that. And then we looked at the behavior of waves. Now, the reason I'm going all the way back here is because now that we're going to be moving into light, we're going to be revisiting these behaviors, because light does behave as a wave at times. And so we're going to be looking at reflection, refraction, diffraction, interference, some of these wave behaviors. So we looked at that, and so we said if you understand how waves work, then you can look at any wave, like sound or light, and you can know how it's going to behave. And so we then did go into sound, and we looked at how sound worked, and did some diagrams on sound, and then we moved into, so we had regular, just what sound was and how they figured it out, the characteristics of sound, same things, the wavelength, amplitude, frequency, speed, and then the the behaviors of sound, just like we did with regular waves, behaving the same way: reflection, refraction, diffraction, interference. So if you have those 4 ways memorized, then it's always easy to apply that to any type of wave. So we looked at those behaviors so we could understand how it works with sound. And then, of course, we tapped into music, because music is part of that sound world, and as the sound world, it had its special qualities, certain things that you could look at: notes, octaves, harmonies, beats, all of those things. And then after the music world, we went into, or we are moving into now, light. And so light is going to have some of those things that we've already talked about, and we'll be able to apply those. So, but thinking about light, so there came a time when men began to be very inquisitive, like about light. What is it? Like, how does it behave? Does it have a speed? Is it infinite? Can it be measured? And there was all this interest in light. And this goes way back, way before the Sir Isaac Newton and the separating of the light in the prism experiment. It was Galileo was trying to measure light. There's many, many men of the past and women who were interested in light and wanted to figure out what it was scientifically. And so it started coming down to two main ways of thought. So there was what we call the wave theory of light, the theory that light was a wave. And the reason that theory was big and why people thought that is because it was behaving like waves. Like we know waves have behavior. They reflect, they refract, there's diffraction, there's interference. It was behaving like a wave, and so therefore was like, maybe it's a wave. Robert Hooke is a famous scientist. You've heard of him before. He did a lot with the microscope and light and all that, but he was looking at the slice of a cork, if you remember back in your life science studies, and he saw that the cork had little box-like things he called cells, and that's where the cell theory of life, some of that originates from Robert Hooke. And so Robert Hooke did a lot with light. Christian Huygens, he also was big in the light world, another scientist and these guys were thinking it was a wave. So Robert Hooke, Christian Huygens, Thomas Young, as you remember when we were talking about wave behavior, when the wave would go through a little tiny hole, and if you had two holes, we called it the double slit experiment, where the wave would go through and it'd start making that weird pattern. Do you remember that? I think it was back when we were talking about, let me see if I can find the picture of it. This one right here, the double slit experiment, where the wave was going through, and then when they were interacting, it would create either destructive interference or constructive interference. Remember that? And so this particular Thomas Young, he's the one who is famous for the double slit experiment. And so he thought it was a wave, was behaving like how waves would through that interference. And then there was James Clerk Maxwell. You probably heard of him anytime you study magnetism, and that is a real big gentleman that you hear about, magnetism, electricity, because he's the one who figured out that really their magnetism and electricity were related. And so in a sense, he united them. And so we realized that magnetism is one side and electricity is another side of the same force. And so they became united as the electromagnetic force. And so James Clerk Maxwell worked a lot with that. Now, when he was doing his calculations for magnetism and electricity, creating this electromagnetic force, these electromagnetic waves, he realized that the speed for his calculations were coming up to be the exact same speed that scientists were figuring out for light. And he said, this can't be a coincidence. This has to be that light has to be electromagnetic wave. And so when you put it together, and I'll just put some color on here so you can see because my drawing's terrible. This is supposed to be a 3D drawing, and that's why it's terrible. I'm not good at that. But say along this axis I have this wave. I'm going to make it red. Okay, and that would be one of the waves, either the electricity or the magnetism wave. And see how I try to make a little line so you can sort of see it. So one wave going that way as it's oscillating, and you remember what oscillation means and propagation when we talked about wave terminology. Oscillation is back and forth motion. Propagation is the movement of the wave. So remember when we had a transverse wave, like say I had a rope and I was shaking it up and down, and then the wave would move this way because it would propagate perpendicular to my up and down moving it, right? So this would be a combination of one set of those transverse waves, which would be maybe, let's make that the electromagnetic wave or the electricity wave or electrical field, and then another oscillation creating this side of it, which would come out of the page, but I just don't do it. I don't have a good drawing sense of it. And that would be the other side, which would be the magnetic field. oscillating. So we have this electricity and magnetism working together to create this united wave, which we would call a electromagnetic wave. And when James Clerk Maxwell figured this out, with the speed of his electromagnetic wave and then the speed of light being that same speed that they were calculating, he said, what this has to be. Light has to be an electromagnetic wave. And so it has the properties. And when we looked at waves, what do we say? What are the properties? You're going to have a wavelength. You're going to have a frequency, right? You're going to have an amplitude, all of those things. And what they were seeing is that light was having wavelengths to a different levels of the light, different wavelengths of light, and then different frequencies. Over time, they figured this all out. And so when they were doing their calculations, this brought light into the wave category, even so more. Then Heinrich Hertz, you've heard of him from the word hertz. That's what we measure some of our stuff in because of him. And he started to find out that with light, there was an invisible side to these waves. So it wasn't just visible light. He started to realize that there were other waves coming from the source of the light that you could not see. And so eventually this became known as what we call the electromagnetic spectrum. And so this, I just sort of drew it out here. And you've seen it before where you got really long wavelength of light, and then it gets smaller and smaller and smaller and smaller to the smaller wavelengths in higher frequencies. And so he's famous for the radio wave, which is the really long wavelength of light that's invisible to our eyes, but it's there. And he was able to create a device to prove it was there. And so that's why Heinrich Hertz is very linked to the radio world. And so when we look at this spectrum, we have radio waves, then we have, which are long, and these microwaves. The farther they get down, the skinnier the wavelength is, or the smaller the wavelength, and the more frequent it's hitting you if it's coming at you. So radio, microwave, infrared, and then there's that region right there that's called visible light, VL I put. And visible light can be separated into the Roy G. Biv. And we'll talk about this on the next page in more detail, but Roy G. Biv is red, orange, yellow, green, blue, indigo, and violet. And this is the part we see with our eyes. But on each side of visible light, our rays are still coming off. There's still electromagnetic waves coming off that you can't see. And so they have wavelengths and they have frequencies. And so he began that discovery. Now, he didn't discover all the rest of these. Different gentlemen discovered or ladies discovered these, but he was linking more with the radio wave and creating a way to prove that it was there, even though it was invisible. And so, again, all these guys are showing, wow, it does have wave properties. It's acting like a wave. It's got to be a wave. But then there was the problem that there was a whole nother group of scientists that were saying, hey, I understand you think it acts like a wave, but it also acts like a particle. And so that brought forth the particle theory. Now, the particle theory of light, a lot of it's linked to Sir Isaac Newton. There was others that thought way before him too, but, there's a few you pick out in your science realm of who added a lot of contribution to the theory. So Sir Isaac Newton, he's the one who would take the light and separate it through the prism. You've seen that experiment before. And so with that experiment, as it separated and the light was diffusing through that medium there, he thought each color was really different particles. He called them corpuscles. He said, when it comes out, the light is separating into these different types of particles, and that's why you see different colors. And what he was linking to eventually is this idea of it being made of more than one thing. And so we don't call it corpuscles anymore or anything, but that's what he started to get us thinking in that direction. Heinrich Hertz, who was also a big, helping us understand the wave side of things and understanding radio waves, he accidentally came across the idea that light was also behaving as a particle, because what was happening is he realized that depending on the type type of light that you would shine on this particular, this is a little box, it's supposed to be like a little piece of metal, okay? So certain metals, if you would shine light on them, if it was light of a high frequency, a very powerful light, some of the stuff that was closer to this end from visible light on, like blue, violet, indigo, all that, that it was powerful enough to actually knock electrons off of the metal, and they proved this. And of course, it had to be above a certain frequency. Now, the lower frequency light wasn't able to do it, but the higher frequency light was able to keep bombarding it and eventually getting enough to where it would free the electron and knock it off the binding of the electron to the atom, and it could go flying off. And the way they figured this out is you could set up a circuit, okay? So this is my circuit here, and I've got my positive and my negative. This is my battery. This is showing pretty much the battery side. I'll just kind of circle it so you see. So I have, with my battery, I have a wire touching this part, and it comes up here, but then there's just a piece of metal here, like say sodium or something, and then this wire right here going through here to another piece of metal. So basically, if you know how circuits work, then these two would have to be touching. If they were touching, then we would have a complete circuit, and you could have electricity flowing through that. But if they're not touching, the circuit wouldn't work. And so this is just like a little measuring of a little measure guy saying whether the circuit's working. I could have drew a little light bulb or something like that. So what they realized is that if you shine light on this metal like this, but it had to be above a certain frequency, so certain light didn't work. You couldn't put just like red light or something on it. It wouldn't work. It had to be of a higher frequency, and you shine it on the metal. Eventually it would create enough to knock off the electron, and the electron would fly and hit this metal and complete the circuit. So with nothing in the middle, as long as you shone light on it, it was making the circuit for electricity. And they said, wait, how can light be a wave, just like one generic kind of wave that's always flowing, if certain wavelengths of light could actually be more able to knock these electrons off? So that began thinking about this being more, that light is kind of more like a particle too. And this is what we call the photoelectric effect. And a lot of scientists worked with the photoelectric effect, and we're trying to figure it out, because it was not, with the photoelectric effect, the fact that different frequencies of light could do it and others couldn't, told us that light wasn't just this one thing. It had some levels to it, and we had to figure that out and how that worked. And so along comes another gentleman who worked with the photoelectric effect, Max Planck. And if you ever heard of Max Planck, his idea was, okay, let's think about this light being energy, okay? Like when we talk about matter, like paper, okay? So when you talk about paper, if you look at paper from just a macro perspective, that means just looking at it with your eyes. I look at paper, it's like, oh, it looks really flat, doesn't it? Paper's flat. There's no bumps to it, paper's flat. But if I put paper underneath a microscope, I realize it's not one big flat something. It's actually small little pieces of something that make up this whole paper. But you can't see that unless you put it under a really high, powerful microscope. And so you look at paper under a high microscope, and it's not flat. It's these little pieces of matter that come together to make the paper. So he said, if matter, meaning anything that has mass and volume, the matter world, like, the table, the book, and everything, if it's made of smaller parts, could energy actually be made of smaller parts too? Maybe on the big scale, on the macro scale, we look at energy and we think it's just continuous. It's all one thing, like the flat paper. But if we had a microscope small enough to see, to get down to the smaller, could energy also be made of small parts? And he said things like, scientists were starting to figure out, like water. Water looks like it's big, one huge thing, but we know that water's made of small molecules of H2O, and they all come and hang out together. And so it's not one big thing. It's made of smaller parts. So the idea was, if matter is made of smaller parts, maybe energy is made of smaller parts. And Max Planck said, okay, it looks like a wave, but maybe it's made of these little tiny
particles. And so this is why maybe it behaves like a wave and it's moving like a wave, but it's behaving like a particle sometimes too. And Albert Einstein is another big scientist who got on board with Max Planck's idea and really unified Max Planck's formulas with the light world and said, hey, this is helping us understand that light is special. It's not one or the other. It's possibly both. And it's what we call the wave-particle duality. That light is so special, it's going to behave in this special unified way between the wave behavior and the particle behavior. And so that's what a lot of people think of as light nowadays. And again, we're trying to figure these things out, and they're very complex, but it does seem like that light could be like a wave and like a particle, and behaving and with both of those characteristics. Now with light in our book, there's a lot of cool things and that we can do some experiments with. Now I'm going to send you some videos with this diagram for some of these experiments, any of them that you could do at home since we're separated right now, to figure out some of these cool properties of light, the way that it will behave. And we've already learned some of these, right? We know this one is representing reflection, the process of reflecting, depending on where you're looking at the reflection is what particular angle and the law of reflection. So I put that on there for us to, I'm going to send you some experiments that show you cool reflection experiments. This one represents refraction. So the reflection is the bouncing off, refraction is the bending of light. You've seen that before when you put a pencil in water, and depending on your view, it looks like the pencil is kind of not in the same place above the water and below the water. So I'll send you some cool refraction experiments that you can do just with water to figure that out, and look at all the cool things that our eyes will see it differently because of the way that the light is moving from the air into the water and changing speed because of that, because when it goes through the water, remember, it slows it down. So I'll give you some refraction experiments. And then this one is just explaining the rainbow world. And the rainbow world, I will also send you a video on. And let me see if I have a purple marker here. And the idea with the rainbow is that in the water droplets, because light is coming, and you know, light can be separated into the different colors. And I'll just do this with the red and the purple, and you could fill in the rest. But when we have our separated light, we have the different colors. Now the thing is, when you think about light, you think that all of these different colors are traveling at the same speed, but the truth is they're not, because they are different frequencies of light. And so different frequencies will travel at different speeds. So it's a small amount of difference, but it's still a difference. And so what happens is when they come in contact with something that they are going to go into a new medium, let's say, and let's see, where's my red? Okay, so I think this is representing the red here. So let's say, okay, this is my light coming in, which let me just use a yellow for that, or my white light, my highlighter. So my light is coming in, and here is this little circle is a raindrop. And so my raindrop is there, and my raindrop's gonna act in a sense like a prism. It's gonna disperse the light, because what happens is when it comes in, even though all of these colors are coming in, red is faster because it has a lower frequency. So the lower frequency lights are gonna be faster through the medium. And so as it's coming in, it'll come in a little faster than any of the other colors. And so when it bounces, and it'll come in here faster, it'll bounce at a different angle than say the purple. And so by the time it gets out of here from reflecting and bounce and then bending and then bouncing back out, by the time it gets here, let's say that's your eyeball, then that area might seem red to me. So in a rainbow, when I have a whole bunch of these drops here and that angle is coming down, I might see that red. But then the purple is also, it's the violet, the other, and all these colors. I could draw all these colors in here bending, but just to be simplistic, red is the fastest and violet is going to be the slower because it's higher frequency. So when it's coming in and it separates into its purple, it bounces at a different angle because it's coming out at a different speed, and so it comes down here. So because my eye is catching that red, I'm not catching that purple. So that area of the sky looks red to me for my rainbow, and vice versa. And so, but maybe like same this water drop, And you'd have to realize that this would be tons and tons of little vapor mist in the air, like right after a really nice rain. And you know how you get a rainbow? That's because it's all that water, the water vapor is trapped in the air. So you're looking at all these reflected light rays from thousands of these water droplets. But let's say the light's coming in here, and let's say my red, which is faster, is going to come in and it's going to bounce and then bounce and it bends here. And remember, my eye's all the way down here though, so my eye doesn't see that part as red. But when the violet is bending and bouncing, then you know my eye picks up that area of the sky as purple. So you end up getting this layering of the rainbow. And so you get the red, you get the orange, the yellow, the green, the blue, and so on. And so you would see in the sky, you'd see sort of this pattern between the angle of the light hitting your eye, which one was getting there from that particular angle, due to the change in the speed, because different frequencies will have just a little bit different speed getting through those particular substances, like the water droplet or whatever. And so that helps us understand the rainbow world. And I'll send you, like I said, a video, because there's even more cool things about rainbows, not just that particular aspect, but even then you sometimes have the inverted rainbow, you have reflections from different, and you'll have double rainbows, and so super cool rainbow stuff. So I'll send you a video on that, and that will give you some ideas. So a couple experiments on reflection, refraction. The reflection and refraction is what is the rainbow world, and dispersion, the light being dispersed out. So that should be good. And then last but not least, we have the electromagnetic spectrum. That's the light that we now know can be divided up for us to understand it more, some that we can see and some that we cannot see. And so we want to just get a little overview of this electromagnetic spectrum world. So what is it? It's an arrangement of all forms of electromagnetic radiation in order of frequency and wavelength. So it's organizing all the light, all the waves that are coming, and putting them in categories so that we can keep track of them in order from frequency, or in order of frequency and wavelength. So all the way down here, like I showed you before, these are the longer wavelengths. So the radio waves, the microwaves, the infrared, and then you got your middle one, which will be the visible light. And we know the visible light is Roy G. Biv. And then some people put indigo in there, so that's why I put I, but some people don't. Either way, it still sounds Roy G. Biv. Yep. Okay, and then we have, on this side of it, we have ultraviolet, UV, and then we have X-ray, and then we have gamma. And so the farther you get down, it's the higher frequencies. And I always say, whenever I teach this, and you'll probably remember, anything on this side of visible light is not dangerous. It's low frequency light. And so it's not frequently hitting you, and it's not going to be damaging your cells as much as anything on this side hitting your cells. This is where it starts to get dangerous. Oops, I almost put a happy face there. But on this side of visible light, UV, X-ray, and gamma, we can be in the presence of some UV, I'll explain, but it's starting to get where it's kind of the danger world. You don't want to be in the presence of that much. Now, again, there was a time when all we knew was visible light. That's because that's what our eyes can see. We didn't know there was more waves on this side and more waves on that side, but here it turns out that there are. And each one of these waves have their own frequency. That's how much they're frequently hitting you. And then they also have their own wavelength, because these are the transverse electromagnetic waves. And so they're the wavelength, long wavelengths or very small wavelengths. That's going to determine good or bad because of how that is coming, and it's entering your cells and all that sort of stuff. All right, so what I thought we'd do is, just as a introduction, because your book gives you a lot of other information too of this, and then it takes these concepts and moves it on to even other cool things about light, like how lasers work and how polarized light works and all that. You're gonna have to do that on your own studies if you're interested, because I don't want us to run out of time here, and we're trying to get through at least this week, and next week I'll probably do one more next week, and then the rest you can finish on your own at home. All right, so with this, let's introduce from this on, from the higher wavelength or the longer wavelengths and the less dangerous, radio waves, what are they used for? Well, things like AM radio, FM radio, your television, regular television, some cell phones too, are used, the radio waves are used as carriers for these things. Microwaves, this is another category, and the microwaves, obviously microwave ovens they use that type of wave to cook your food, but then also the communication satellites. And down underneath the communication satellites, I put TV, radio, and cell phones too, because you have your satellite TV, your satellite radio, your satellite cell phones, and so you can, both of these guys go back and forth with the cell phone world. GPS uses the microwave region of the electromagnetic spectrum. Radar uses the microwave area, which would be this particular area here. All right, and then there's infrared waves. And infrared waves, what they are is they're basically, if you look at them, the IR, it's right on this side of visible light. So right after infrared is the R. And same with after the Roy G. Biv violet, you have UV, which is ultraviolet. So infrared means an inferior red. It's a wavelength that's a little more inferior to the real wavelengths of red. And so it's called infrared, meaning inferior red. And so this wavelength is where we use a lot for transmitting heat. And even our bodies will emit infrared out. That's why if you look through the infrared cameras, it looks like somebody's warm. You can tell where their warm spots are. So this is related a lot to the heat, and special cameras can detect that. Ultraviolet. So ultraviolet is the next one after visible light. Now I skipped visible light, and the reason I skipped visible light is because we've already talked a little bit about visible light, and we know the colors of light and all that. So I'll probably put just the colors right down here in the middle to separate that, and I'm going to have a little rainbow visible light craft for you for the next page. And so, but after visible light, then we move on to ultraviolet. Ultraviolet is the are waves that we can't see again. So all 6 of these are we can't see you. And then the middle one, visible light, is the ones we can see. Now we can detect these with special detectors, but we just can't visibly see them. Okay, ultraviolet. So again, since it's on this side of Roy G. Biv, right after violet, it's a little better than violet. It's a superior violet. It's an ultraviolet, and so that's how it gets its name. So and with ultraviolet, we have UVA, UVB, UVC. So there's categories among this UV because there's different wavelengths in that whole category of UV. And so if you're UVA, that's not as dangerous. Still, even though it's on this sad category here, the farther it goes down in its category towards X-ray is when it's starting to get not so good. So we categorize UVA as kind of closer to the V, the regular violet, and that is like the black lights and stuff that we use that aren't too dangerous. UVB, that's the light you can use like for tanning beds and stuff, but that's what gives you sunburn, so that can get a little dangerous, too much exposure of that, right? And then UVC, that's the most dangerous category of the UV, and that is the stuff we don't want, but thankfully our ozone blocks that out. So that's going to be nice for us, so we don't have to be in contact with that. Now UV can be used to sterilize things. UV is important. We do have to get some UV because it helps us with synthesizing the vitamin D. And then there's the X-rays. Now the X-rays are called X-rays because when they were discovered, Wilhelm Röntgen, when he discovered them, when he was working with a Crookes tube and he was looking at, how things were interacting in that particular Crookes tube, that's another lesson for itself, he realized that there were some rays still coming off of the Crookes tube even when it was covered, and it was these mysterious rays that were lighting up some material in his lab that had the property for phosphorescence. and or fluorescence. And so he said, what are these rays? They're invisible, but I know they're coming off because it was still lighting up the material. Even if he closed the door and had these rays that were being emitted from the Crookes tube that he was using, he knew that there was something, there were these mysterious rays, and he called them X-ray because they were mysterious. And so, if you don't understand something, you put an X there, like in algebra. If you're trying to figure out something and you're like A plus B equals, and you don't know, you put X, like mysterious. We got to figure it out. And so that name stuck, X-rays, and what they can be used for, obviously broken bones imaging, so you can look inside the body, because the X-rays can go through more things than normal wave rays can. Gamma rays, the most powerful and the most harmful of this particular category, and they are not, you do not want to be in the presence of gamma rays, and so gamma ray radiation is bad. However, if we can use it medically if we hone in to only making the rays to be where they're only going to be shot at things like cancer cells or something like that. So we can use this for good, but in just a regular emission of electromagnetic radiation, you don't want to be in the presence of the gamma rays. And then you can also use it in, just like sterilizing things with UV, you can use it for trying to kill off anything that might be on something, like, say for instance, a bandage or something. If they got to make the bandages so clean that when you put it on your cut, that it doesn't have any microorganisms or something growing or already on it that you didn't know. And so irradiators they're going to use this radiation to shoot at things like that need to be very, very sterile, so bandages and such. Sometimes they use this even in food processing with the gamma rays. They shoot these powerful rays at food that's going to go into cans so that it can be, you can make sure there is no microorganisms growing in there that's going to make anybody sick. So there's some ways we can use the gamma rays. So these six main, plus our big guy in the middle, the visible light spectrum, is giving us an overview of what light is in the area of it being electromagnetic waves and put onto electromagnetic spectrum. Now, as you see here, I have this little note for myself, visible light craft. That's because in that little spot, what I wanted to do is I wanted to do some sort of art thing just to kind of make it a little more exciting, because I know we're separating, we can't do any of the real fun stuff that we like to do. So I thought, well, what I'll do is I'll just make a little visible light, which would be Roy G. Biv craft. And so I looked up, I found an artist who does a bunch of rainbow type art. She does all kinds of things, and this is one that she's going to do, but it's not the one you have to do, because I will send you the video, and she makes rainbows out of cut pieces of paper. She makes them out of cut from magazines, paint, watercolors, but this one I'm gonna do, she just took like a drop of each one of the colors, and then she just smeared it with whoa, that was interesting amount. So if you have paint at home and you want to do this one's kind of easy, but I'm just trying to make some sort of craft that is gonna be something for our journal that it gives us a visual of visible light, which is that middle guard between the two sides of the electromagnetic spectrum. And of course, whatever kind of paint I find here at the Science Center, it's always interesting. I don't know how long it's been here. I don't know where it came from sometimes. So sometimes it's goopy, sometimes it's great, who knows. But she took these colors of the rainbow, and she just did a little squirt of each. And like I said, this is not the one you have to do. You can do a glue one, you can do a watercolor one, and whatever, but I would love for you, when you do it, to then send me a picture of it too, along with saving it for the journal, because once it dries, I do want to glue this in your journal, so you do need to do it on a half sheet so it'll fit there. But what she did is she took these colors for the rainbow, and then she just took, like, I don't know what she was using, a knife or something like that, or a piece of paper. I just took a piece of paper and folded it over to make it like firm, and she just smeared it. She just did some smear paint and just kind of kept the rainbow. I thought it was really pretty. But you'll see it in the video. Now I gotta push down, and I think she just kind of did something like this, and it was super cool. I'm gonna try it one more time and see what I can
Oh, don't get it all smeared, Miss Jody. Okay. But I really like that. Oh, I like that little wavy thing, because then that can remind me that light sometimes behaves like a wave and a particle. So wow, that turned out really good. Okay, so I'll send you the link on some of her art so that you can pick what you want to do. It doesn't have to be that, but I really like how that turned out, though I've got paint all over my hands now. So, but I'll let this dry, and then I'll glue that in the journal, and that will be right for the end of this chapter. So like I said, there's a couple other things on how lasers work and polarized light and all that. If you want to go and read that, again, this book was a really high level book, so I pick and choose on some of the things that we do, and there's only so much time. So you don't have to, but if you want to look at anything else, the speed of light, how they figured that out, and general relativity and all that is in there, but that's kind of high level learning. So whatever you decide. And then our next chapter is the history of or basically electrostatics, and that's just going to be basically how electricity and magnetism work, and that'll be kind of cool. So I think we'll probably end with those. Let me see what's the next chapter after that, because I don't want to go too long. Oh, it's still on electricity and the currents, current electricity and static electricity. So maybe we'll do a little bit with that. So we'll see. It'll either be one more video or two more videos. And then the last chapter is just on electronics, was showing us how we can use all these things with electricity and magnetism and light and use them for our own good. Okay, so I miss you guys, and I still hope to see you soon. Make sure you send me as many pictures as you can. I love seeing you. I've got some good pictures from some of you and some videos, and it's made my day. See you soon.